at the point where we can derive the fundamental theorem of line integrals. That's what this section is all about. The goal is to evaluate line integrals with respect to vector fields using FTLI, the fundamental theorem of line integrals. I don't know if you noticed, but in the last section, some of those line integrals with respect to vector fields can be pretty long in terms of setting it up, right? And then maybe you might get a long evaluation of your integral too. There is a shortcut to evaluating these things. It turns out there's a much easier way to compute the line integral over a vector field. So let's derive it. It won't take all that long. Let's think about the symbolism for just a generic line integral f dot dr. Now, if f is conservative, you can rewrite this as the integral over c of del f dot dr, just substituting what f is equal to, capital F is equal to del f. And then we're going to put in component form both of these vectors. So we're going to rewrite this as the integral over c of del f. Well, del f is a vector of partials, f sub x, f sub y, f sub z. These are partials with respect to x, y, and z, respectively. And then remember what dr is? It's a vector full of differentials. Remember that? I'm just rederiving differential form for the time being. That's all I'm doing. Nothing new here. And then we get the integral. I'll keep it over c of, what is this, f sub x dx. Well, okay, technically when you write it this way, I suppose you could put in limits of integration. I'll go ahead and do that all right now, I guess. Because really, we're thinking of r of t as a parameterization for c, and when we write it this way, we're thinking of all those partial derivatives as being in terms of t, and dx and dy and dz being in terms of t. So you can make it your integral from a to b, t equals a to t equals b. Okay, do the dot product, f sub x dx plus f sub y dy plus f sub z dz. And this is really just differential form all over again, right? I didn't have to derive all this again, but it doesn't hurt to see it twice. Before, we didn't know for sure if f was conservative, so instead of seeing f sub x, f sub y, f sub z, you saw p, q, and r, respectively, dx, dy, and dz in the differential form. Okay, but when f is conservative, this is a very special quantity. But there's a lot of information in this class, so you may not remember what that quantity is. That quantity is the total differential. Does that ring a bell from a couple of chapters ago? It's the total differential. We have a notation for that. Remember dz or df? So I'm actually going to call this df. It's the total differential. But it only works to write it this way. It only is the total differential if f is conservative. Oh, so I'm actually going to rewrite the integral as the integral from a to b of df. Now that doesn't tell me much, so let's put in the differential dt, and we know that the differential behaves algebraically. So you may not understand the full machinery of what's happening here, but you know notationally dt behaves algebraically, so I'm going to multiply by dt, divide by dt. So in the integral, what have I done? I've turned the integrand into a calculus 1 type function. df dt is a single input function, right? And not only is it a single input function, it's a derivative. What do integrals and derivatives do to each other? They knock each other out. And in fact, by the fundamental theorem of calculus 1, we can evaluate this. What's the antiderivative of df dt? It is f, but let me be specific. It's f Okay, remember, it's f of x of t, y of t, z of t. But ultimately, when you write x, y, and z in terms of t, which is what this notation means, that is a single input function in terms of t. And then you have to evaluate it by the original fundamental theorem of calculus from a to b. So those are evaluation brackets. And so by the original fundamental theorem of calculus, we can say that, okay, plug in the upper value for t. This is equal to f of x of b, y of b, z of b, minus f of, plug in the lower limit, f of x of a, y of a, z of a. To make it look even more like the original fundamental theorem, you can remember that if r of t is your parameterization for your curve, then this is really just r evaluated at b. X of b, y of b, z of b is really just the point generated when you plug b into your r of t, your vector valued function. And x of a, y of a, z of a is really just r of a. And so we're saying, another way to write the formula is that the value of that integral, that line integral, is f of r of b minus f of r of a. And that really is reminiscent of the original fundamental theorem. But there's a way I like to write it in, as well, I want to say in using words, but it's not all words. It's symbolism combined with words. This is, if you think about the curve, if it's oriented this way, and r of t gives you a parameterization for it, then this point might be, or is, r of a. This point over here is r of b. I like to think of r of a as the initial point, or maybe beginning point, if you like. And r of b as the end point. So what this is really saying is that if you want to evaluate the line integral, just to remind you what we were doing, when f can be written as the gradient of a scalar function, then this is equal to f of the endpoint minus f of the beginning point. That's kind of a nice way to think about the fundamental theorem of line integrals. What this is really saying is the curve between the beginning point and the end point doesn't matter. Isn't it? Isn't that what it's saying? As long as f is conservative, you could take this curve from r of a to r of b, or you could take some crazy curve, doesn't matter, from the same beginning point to the same end point, and guess what? You're going to get the same value over either curve for the integral. It's going to be f of the endpoint minus f of the beginning point. The integral is independent of path.